Good morning, everyone. We are the quartet from Group 3, and we're going to continue the reporting about Unit 2, Leveling, which consists of the following topics: three-wire leveling, curvature and refraction, trigonometric and stadia leveling, and the common errors and mistakes of leveling. I am JC Ray Salvador, and I will be tackling three-wire leveling. Three-wire leveling is a method of determining differences in elevation wherein three horizontal hairs are read and recorded rather than a single horizontal hair. This allows the surveyor to immediately verify whether the readings are correct. Therefore, three-wire leveling is a more precise method of differential leveling. What you see in the screen right now is an example of a stadia hair or the crosshairs in an instrument used for leveling such as automatic level. So we have here the three horizontal hairs referred to as upper reading, middle reading, and lower reading. The middle reading is also considered as the rod reading. The process for three-wire leveling involves taking the average of three readings, the top crosshair, middle crosshair, and bottom crosshair. The average of the top crosshair and bottom crosshair should be about equal to the middle crosshair. Moving on, in order to compute the readings for three-wire leveling, here are the following variables you need to take note of when computing, where A is the upper stadia hair reading, B is the lower stadia hair reading, C is the horizontal intercept or the difference between the upper stadia hair reading and the lower stadia hair reading, M is the mean or the average of the three hair readings, HD is the horizontal distance from the level to the rod held at P, K is the stadia interval factor, C is the instrument constant, HI is the height of the line of sight above the datum or simply the height of instrument, and LF of P is the unknown elevation of station P. In order to appreciate and understand the equations and variables, we're going to answer a sample field note which consists of the given readings per station as well as the elevation. Now the first process is to solve all the mean readings of the back side, then followed by the mean readings of the far side. And by the way, as a recap, backside reading is a reading on a point of a known elevation, while far side reading is a reading on a point of an unknown elevation. In computing for the mean reading, we are going to get the sum of all three readings and divide it into 3. Using our calculators, we're going to solve for the mean reading. For BM1, we have 0.935. For TP1, we have 2.420. For TP2, we have 1.440. For TP3, we have 2.095. And for TP4, we have 0.730. Using the same formula, we're going to solve now for the mean readings of the far side. So we have 0.899, 1.536, 1.177, 1.714, and 1.410. After computing for all the mean readings, we're going to get the stadia, which is abbreviated as S, by subtracting the upper reading from the lower reading. But first, how do we determine what reading is the upper, lower, or middle by just looking in the field note? So the first reading in a particular station is the upper reading, then followed by the middle reading, which is of course located in the middle, and the last one is the lower reading. So again, the formula for getting the stadia is to subtract the upper reading from the lower reading. So for BM1, the stadia is 0.434, followed by 0.727, 0.547, 0.992, 0.366, and for the far side, we have 0.435, 0.728, 0.546, 0.992, and 0.366. So at this moment, we already have all the mean readings and stadia of both backside and far side. Now it is time to compute the HI or the height of instruments. In finding the HI, we need the presence of the elevation. So going back to our formulas, we have here the formula of the unknown elevation of P, which is HI minus M. But in our field note, we have observed that the elevation of P is already given. So we just need to derive the formula by transposing the M or the mean readings to the other side. Thus, to get the HI, we just need to add the elevation and the mean reading. So for the HI of BM1, we just need to add the elevation, which is 444.242, to the mean reading of the backside, which is 0.935, and we're able to get 445.177. But going to the next location, we can see that the elevation and the HI is not given. In that case, we are already going to use the formula of elevation by subtracting the HI to the mean reading of the next location. So again, we're going to subtract the HI of the previous location to the mean reading of the next location, or the mean reading in the far side. So the elevation for TP1 is 444.278. So if you're wondering why we compute for the elevation first rather than the HI, it is because if we're going to recall, we need the presence of the elevation in order to compute for the HI. So after getting the elevation, we just repeat what we did in the first station until we complete the field note. So we're going to add the elevation and the mean reading, and we are able to get 446.698. Then next is to subtract the HI to the mean reading of the next station, and the result is 445.162. Then add again, the result is 446.602. Then subtract 445.425. Then add 447.520. Then subtract, the result is 445.806. Then add again 446.536, and lastly subtract to be able to get 445.126. In order for us to check if the computations are accurate, we do the arithmetic checking. So we have here the summation of the mean readings of the backside, which is 7.62, the summation of the mean readings of the far side, which is 6.736, and the given elevation of the field note, which is 444.242. So using this formula, we have the summation of the mean readings of the backside minus the summation of the mean readings of the far side, and the result, we're going to add it to the given elevation. So 7.62 minus 6.736, we have 0.884. Add it to the given elevation, which is 444.242, and the result is 445.126. And we're going to compare it to the elevation we were able to get in the field note. So the last elevation is 445.126. That means our computations are accurate. As a summary, here is the process in computing for 3-wire leveling. So first is to solve all mean readings of the backside, then followed by all mean readings of the far side, then solve all stadia of the backside and all stadia of the far side. Then solve for HI. So in HI, we need the presence of the elevation and the mean reading. And lastly, solve for elevation, or HI of the previous station minus the mean reading of the station we are finding. So we are just going to repeat the process of solving for HI and elevation interchangeably until you finish all the stations.
I am Monica Biancati Caballos, and let us proceed to the curvature and refraction. So curvature and refraction affects any measurements dependent on an optical line of sight, or the LOS, or energy wave, which is quite a few. For long sights and accurate leveling work, the effects of curvature of the Earth and refraction of the line of sight shall have to be taken into consideration. So what is curvature? So the Earth has a curving face that is considered to be a level surface, yet the leveling instrument's line of sight is horizontal, not the level line. Thus, the Earth's curvature causes a rod reading taken at point B to be too high. As a result, all locations on the line of sight are not equidistant from the Earth's surface, and the points read on the staff are not exactly at the same level as the diagram's horizontal hair. The level line deviates from the horizontal line of sight, and the vertical distance between the horizontal and level lines indicate the Earth's curvature. The effect of curvature is to increase the staff reading or the rod reading, and error increases exponentially with distance. So we have here K as the length of sight or the distance from the instrument to the staff station in kilometers. BC, with the green arrow as seen on the picture, is the error due to curvature. O is the center of the Earth, and R is the radius of the Earth. So to solve for the curvature correction, we have these formulas where the constant will be different depending on the units intended for the solution. If K is in kilometers, then we have C is equals to 0.07849 times K squared. If K is in miles, then C is equals to 0.667 K squared. If K is in feet, then C is equal to 0.0239 times K squared. For example, we have find the correction for curvature for a distance of 2.48 kilometers. Since we know that K is in kilometers, then we will use the formula C is equals to 0.7849 multiplied by our distance, which is 2.48 kilometers squared. So the answer would be 0.483 meters. Let us proceed to refraction. Refraction is a well-established law of physics that rays of light passing through layers of different densities do not remain straight but are refracted or bent down towards the denser medium. This bending is referred to as refraction. That includes the LOS through the instrument's telescope. The denser the atmosphere, the more LOS is bent. This is affected by temperature, atmospheric pressure, and geographic location. When seeing longer distances, our LOS begins at the density condition of the device and bends downward as it passes through a progressively denser atmosphere towards the target. Refraction correction is about 1/7 the effect of curvature but in the opposite direction. To solve for refraction correction, we have these formulas wherein, again, the constant will be different depending on the units intended for the solution. If K is in kilometers, then we have C is equal to 0.011 multiplied by K squared. And if K is in miles, then C is equal to 0.093 multiplied by K squared. And if K is in feet, then C is equal to 0.033 multiplied by K squared. For example, we have find the correction for refraction for a distance of 2.48 kilometers. Since 2.48 or the distance is in kilometers, then we will use the formula where K is in kilometers. So we have C is equals to 0.011 multiplied by the distance of 2.48 kilometers and squared. We have 0.068 meters. Now for the curvature and refraction, they are sometimes viewed as a single combined correction since they are interrelated, yet their effects are completely contrary. Since the effect of curvature is to increase the staff readings and that of refraction is to decrease them, and also the effect of curvature is greater than that of refraction. The combined effect is therefore to increase the staff reading, hence the combined correction is subtractive. The combination of the Earth's curvature and atmospheric refraction causes the telescope's line of sight to vary from a level line by approximately 0.0785 minus 0.0110 or 0.0675 meters in 1 kilometer. Curvature error is the vertical distance from an assumed horizontal line to the actual ground surface, while diffraction accounts for the amount of the LOS of the instrument was bent from that horizontal line. Using Pythagorean theorem, we can relate the curvature error c in feet to the radius of the Earth and the horizontal distance. To solve for the combined correction, we have these formulas where again constant will be different depending on the units intended for the solution. For example, we have find the correction for curvature and refraction for a distance of 1.29 kilometers. So for the formula with k in kilometers, we have c is equals to 0.0675 multiplied by its distance, which is 1.29 kilometer squared. So the answer would be 0.112 meters. Now let us have an illustrative problem. A woman standing on a beach can just see the top of a lighthouse 24.140 kilometers away. If her eye height above sea level is 1.738 meters, determine the height of the lighthouse above sea level. Now, we know that their total distance from the woman to the lighthouse is equal to the distance of the woman to the point of tangency added to the distance of the lighthouse to the point of tangency. And to get this distance is we have the square root of their height divided by 0.0675. Since we don't know the height of the lighthouse, we have to derive the formula, and we have here the square root of height of the lighthouse divided by 0.0675 is equals to their total distance, which is 24.140 kilometers, minus the square root of the height of the woman, which is 1.738 meters, divided by 0.0675. Now we eliminate their square root by squaring both sides, where we have the height of the lighthouse divided by 0.0675 is equals to the 24.140 kilometers minus the square root of 1.738 meters divided by 0.0675 squared. And now, since we only need the height of the lighthouse, we need to multiply 0.0675 on both sides, which led us to each L is equals to 24.140 kilometers minus 5.0742 meters squared multiplied by 0.0675. So height of the lighthouse is equal to 363.504 multiplied by 0.067, and we got 24.53652 meters or 24.537 meters. So here are the ways on how to eliminate error due to curvature and refraction. So proper field procedures. Taking shorter shots and balancing shots can practically reduce errors. Next, we have the staff reading should be kept at least 0.5 meters above the ground. Then using short observation distances like 25 meters equalized for a backsight and foresight. Then the air below is denser than the air above. Line of sight is bent downward, which negates Earth curvature error by 14%. Simultaneous reciprocal trigonometrical heightening is also useful for precise height determination. And lastly, the observations made at each station at exactly the same time helps cancel the effects of curvature and refraction.
Good morning everyone, I am Christian Ayapa of Group 3. I will be reporting about trigonometric leveling. First, let us define trigonometric leveling. It is the process of determining the different elevation of station from observed vertical angle and known distance. So, breaking down the definition, our goal is to determine the different elevation of the station using the vertical angle, which is measured by means of a theodolite, and the horizontal distance, which can either be measured or computed. So, trigonometric leveling is then used in areas of very steep or rugged terrain, or when there are points that are hard to access, for example, in the mountains. To get a quick idea or image about this type of leveling, let us view this quick video showing the setup. The instrument is placed at point A. While the rod is placed on point B. So this is the rod. The instrument is used to obtain the vertical angle. This video will give us a little glimpse of how this type of leveling will look like. Finally, here is the 2D view where we can see the important measurements, which are HR, delta E, S, Z, H, V, and HI. But don't worry, we will be talking about that more later. So proceeding, here is the illustration, which is similar from what we have seen earlier. This illustration is for trigonometric leveling in short lines, which means we will be disregarding curvature and refraction. For us to solve the change in elevation, we must first learn how to solve for V. If S and the vertical angle are determined, we will be able to solve for V. Let us identify S, V, and the vertical angle in the illustration. So this is S, V, and the vertical angle. Identifying them will make it easier for us to understand the formula because the concept of SOHCAHTOA is applied. As we can see, V is the opposite and S is the hypotenuse. And the vertical angle is here. So, since we are applying trigonometric concepts, SOHCAHTOA, the concept of sine, which is sine is equal to opposite over hypotenuse. So, our opposite is V and our hypotenuse is S. So, cross multiplying that, we will be able to arrive at this formula, which is V is equal to S sine alpha. Or we can also use cosine, where we will get V is equal to S cosine Z, where Z is this angle right here. On the other hand, if V and H and the vertical angle is given, the formula will be V is equal to H tan alpha. The same trigonometric concept is applied, but instead of using the opposite side, instead of using the hypotenuse, which is S, the adjacent side H will be utilized. And now that we have the formula for V, we can now proceed. To solve for that, our goal is to determine the change or difference in elevation, which is given by the formula change in elevation is equal to HI plus V minus R, where HI is the height of the instrument above point A. and R is the rod reading at B when the vertical angle is read. But it is important to note that these equations are only applicable when shots are taken at less than 1,000 feet. Shots exceeding 1,000 feet must take into consideration the effects of curvature and refraction, meaning we won't be able to use the mentioned formulas. To continue, we will be talking about trigonometric leveling procedure with long lines. Our formula will be quite similar with the previous formula for change in elevation in short lines, which is hi plus v minus r. But with the addition of the value 0.0675 k squared, this is the combined correction. We have this because we are now dealing with curvature and refraction. But aside from this formula, there is another technique in solving for the change in elevation. So the effects of curvature and refraction can be eliminated if the vertical angle observations are made simultaneously at both ends of the line, such as at points A and B. So this means that if we can provide the vertical angles from both ends of the line at points A and B, we can then disregard the effect of curvature and refraction. But how so? Well, the technique is called reciprocal vertical angle observation. When we apply this concept, we can simply disregard the effect of curvature. So as you can see in the illustration, we have two angles which are alpha and beta. Alpha is the one in color yellow and beta is the one in color green. The angles come from the ends of the line, which are points A and B. Change in the formula used for this technique are change in elevation is equal to h over 2 times tan alpha plus tan beta, or change in elevation is equal to s over 2 times tan alpha plus tan beta. H and S can be interchanged since, as we can see in the illustration here, H and S is quite the same. So in this formula, alpha is the vertical angle taken from A to B and beta is the vertical angle taken from B to A. Let us have this simple sample problem where the reduced level at rod is being asked. We will be applying the formulas we have discussed earlier. For this problem, curvature and refraction can be disregarded since it is a short distance example. So in the sample problem, we are given the height of the instrument, the rod reading, and the reduced level station or the elevation. In order to use the formula RL at rod is equal to RL station plus HI minus V minus rod reading, we must first solve for the V, where V is equal to sine 30 degrees 22 minutes multiplied by 82.18. So solving for that, V will be equal to 41.54 feet. Now that we have the value for V, we can now solve for the reduced level at rod, which is equal to 361.29 plus 4.72 minus 41.54 minus 4. So after computing, our answer for the reduced level at rod is equal to 320.47 feet. That will be all for trigonometric leveling. Thank you.
Hello everyone, and my name is Selwyn Kyle Batad, and I am here to talk about stadia leveling. So the stadia method provides a faster method of leveling in rough and hilly terrain, where a high degree of precision is not required. So this process involved is very identical to that in differential leveling. That the main difference is that the line of sight in stadia level does not have to be brought to a horizontal position as in differential leveling. So from the figure shown, that is the principle of stadia. So from similar triangles of the figure, we can derive from this formula. So d over f is equals to the stadia interval or intercept over the distance between stadia hairs. So thus d is equals to ks plus c. So f, uppercase f is the principal focus, while the lowercase f is for focal length, o for optical center, I for the distance between stadia hairs, c for the distance from the optical center to center of instrument, and s for stadia interval or intercept, and k or f over I is the stadia interval factor. So as you can see in the figure, the instrument is not placed on a horizontal position, so that is stadia leveling. We can compute that by this given formula. So where VD is equals to vertical distance, K for stadia interval factor, S for stadia intercept, and C can either be the distance from the center of instrument up to the principal focus, or for interval focusing telescope it is 0. And for DE is the difference in elevation, and RR for rod reading in the middle. Sample problem. So for our sample problem, let us complete the stadia level notes shown below and perform arithmetic check. Let us assume that our stadia interval factor, which is RK, is 100, and our distance from the center of the instrument is 0. So let us find the vertical distance for both backsight and foresight, and their difference in elevation and elevation. So for the backsight, the vertical distance are as follows: 9.56, 11.86, and for the foresight, 21.64 and 8.55. Now for their difference in elevation, which is 32.07, negative 22.39, and for the elevation is 107.07 and 84.68. So for the difference of elevation, we got it from this formula. So the rod reading of the backsight, which is 2.42, and the vertical distance of the backsight, which is 9.56, plus the vertical distance of the foresight, which is 21.64, and the rod reading for the foresight minus 1.55. So that is the differential elevation of TP1, which is 32.07. As for PM2, which is the rod reading of the backsight, which is 1.08, minus 11.86, which is the vertical reading distance of the backsight, minus 8.55, the vertical distance for the foresight, minus 3.06, which is the rod reading for the foresight. So that is negative 22.39. So this is the illustration for the sample problem. So as you can see, the blue line represents the difference of elevation, and the red line represents the vertical distance. And that would be all for stadia leveling.
Hello everyone, I'm Vincent Ruffles and I will discuss about the common errors when performing leveling. A discrepancy is defined as the difference between two or more measured values of the same quantity. However, measurements are never exact and there will always be a degree of variance regardless of the survey instrument or method used. These variances are known as errors and will need to be reduced or eliminated to maintain specific survey standards. Here are some of the common errors you will be encountering. First is misreading the rod. This happens when the instrument man reads the rod incorrectly. As we all know, the instrument man is the one who is assigned to operate the surveying instruments. This mistake most frequently occurs when the line of sight of the rod is partially obstructed by vegetation or other objects in the field. Example would be surveying in a grasslands. Next is incorrect recording. The recorder should always call out the readings as he records them in order to prevent the recording of incorrect values. Mistakes usually happens in recording as one would write the number 9 as 6 or the other way around, writing 6 as 9, writing 8 as 3 or vice versa. One would also interchange the position of the given values. Example like 1.87 and the recorder would write it off as 1.78. Calling the recorded value once written will act as a review and the other members of the team could correct the mistake that you have written. Next is erroneous computations. Although level notes only require simple additions and subtractions, mistakes in these computations are still committed. With a lot of numbers and data to be added, one could omit a value in the middle or inputting the value twice, which could result in an error. Example, adding 8 backsight or 8 foresight values and only inputting or solving 7 or even 9 of these values will result in an incorrect answer. For this reason, a mathematical check should always be performed to ensure that only correct values are determined. Next one is the rod not fully extended. It is important that the rod is fully extended when reading the high or long rod. The two sliding sections should lock properly into position. The clamp should always be tightened firmly to avoid the upper portion of the rod from sliding downward. It is a common mistake when extending the rod and simply assuming it is fully extended since you felt that it is already hard to pull. One should always check the clamp to ensure it is fully extended, or the readings will be off the mark by length of the portion that still remains uncovered. And lastly, moving turning points. A turning point carelessly or accidentally moved out of its position by a rodman will cause a serious mistake in leveling work. This mistake could be prevented by using only stable and clearly defined turning points or by marking the position of the rod with paint, lumber crayon, or chalk. Not having marked the position of your turning points when the rod accidentally slipped by your hand and assume another position after picking it up, as you only mark the turning point with only a little stone to begin with. During the calculations, there would be a difference in the measurement that will cause you to repeat your observations. And those are the common errors you will encounter in performing leveling. All blunders must be found and eliminated prior to submitting a survey for inclusion in the project mapping. The surveyor, or yourself, must remain alert and constantly examine measurements to eliminate these mistakes and blunders. These blunders or mistakes can be detected and eliminated by reacting to the messages by the data collector when they occur.